Welcome everyone, and today we are happy to have Anton back as a speaker of ITMP seminar, and he's going to speak about supersymmetric CPN deformations of conformal limits and conformal limits. So please go ahead.
Yeah. All right. Thanks for the invitation. Today I'd like to talk about supersymmetric deformations of the complex projective space sigma models and discuss the special conformal limits which arise as new models themselves. So let me start with a slight deviation with the motivations. So the reason for studying such constructions stems from a variety of problems, and some of them include formulation of the chiral approach for supersymmetric sigma models, and what it means I will try to make more precise during my talk. And so another question would be related to the supersymmetrization of the sigma models on different geometries. Another point would be relating the anomaly cancellation mechanisms and its interpretation on the 2 points from above, and especially separate important subfield is an investigation of the exact beta functions, which especially arise in supersymmetric models, not only restricted to 2 dimensions, but also in higher ones. And of course, finding the geometric interpretation and geometric limits for such models that stem from the QFT description. So, okay, since I was asked, let me recap a few basic constituents, including what the sigma model is. Well, this is field-theoretic configuration setup on the curved manifold that stems from this mapping, where sigma is a certain space that is embedded into the larger target space, which I call curly M. And such theoretic setups, they arise in a variety of different subfields, including string theory, where these models in principle live on the 2-dimensional wall sheet, but in principle it doesn't need to be, because one can also look into dimensional reductions of different kinds, and this would stem in general to constitute like a Wald volume. Then it also arises in the what is called lower energetic descriptions in effective field series and CMTs. And in principle, generic, since I'm mainly focused on the aspects that are related to the conformal field series and string theory, I'm interested in 2-dimensional models. So effectively, the ones that, as I mentioned, are defined on the wall sheet. The generic action of such model stems from the Lagrangian that can be defined in this way, which is, as you can see, quadratic in the fields or coordinates on the aforementioned target space, where these capital X are coordinates on this higher d-dimensional, in general, Riemannian manifold. And in the first term, this is the metric of the full target space, and H's, according to the string theory, correspond to the geometry description of the wall sheet. And in principle, we can have additional terms, all kinds of not restricted to this, like a B field, which is again a metric which is taken this form. In principle, it can be generic. One can also add a variety of topological terms, like tachyonic terms and more. My particular interest in this secular is devoted to the deformations of these wall sheet integrable sigma models, where integrability, I will explain how it emerges and how it can be provided based on the symmetries of the model. Also, a generic statement, or like there is no unified statement whether symmetries can guarantee you integrability in general. So one of the canonical deformations at the so-called classical integrability level are the so-called trigonometric or elliptic deformations, and an example of this can be Fateev-Onofri-Zamolodchikov model, which is a conventional example of the trigonometric deformation. And in principle, it is taken this form where, as I said, this contains two types of the fields and two parameters, which are parameterized by one unified parameter. They control the so-called geometry of the space. I'm referring to this A and B. In general, these are the ones that get renormalized. And according to this model, the RG equation to one loop is taking this basic form, and due to this quite vast symmetries, the RG equation can be reduced to this couple on A and B that arise in the action. So in principle, these two parameters that describe how geometry is deforming. As I said, the geometry itself can be written in this compact form where you have a metric times the so-called U field, which is characterized in the bosonic degrees. The fact is that this part describing geometry can be recasted in slightly different form, which we find more convenient. I'm just bringing in the forms that will be important for the later notes. So this kappa and S play the role of A and B in the previous work, which are related through certain map. But at the same time, this mapping allows us to reduce this RG equations to the absolutely basic form, where this physical interpretation of the RG flow is almost immediate. Where maybe I apologize if it cannot be seen very well, but what I want to demonstrate here, this is this parameter S plotted against kappa at different kappa taken different kappa values, and this exponential decay is a certain time slice, as you can see, to this Cauchy initial problem. What is important here to see is that when S is 0, it corresponds to the so-called cylinder model on the cylinder, and this UV from the S0 flows to IR, where the so-called, another name for this Fateev-Onofri-Zamolodchikov, this so-called sausage model reduces to a sphere, as you can see, because of this CP1.
So for the previous slide, so you get X and Y's. So this means that your, like, let's say, target space is two-dimensional.
Well, yes. In this case, yes. Here on the first slide, it is just generic definition, as you can see. And
then what is G here? You just extract the prefactors, right?
Assuming G is a metric.
How do you read off G from the action?
From here, you understand and you can derive this geometry.
No, I'm asking. So you had the action, and I guess. So is there any G in the?
You effectively, well, Mitya, effectively you are solving this equation, as you understand, right?
No, I think Mitya is asking about. You wrote this Lagrangian. You interpret this as a sigma model on a target space.
Yes.
And from Lagrangian, you see what's the target space metric, Gij, if you compare it to general sigma model.
If you look into this definition, yes, but
yes.
That's how what does your geometry defines for you?
So it's the metric of a very special type, right? So
yes, of course. This is what I'm restricting. As you can see, I'm saying that this is here. This is CP1 target space.
Okay, thank you.
Yes.
I also have a question. What is T on the previous slide?
Sorry, this T?
This T.
Yeah, sorry, I'm not saying this explicitly, but this is like a parameter that unifies. This is hyperbolic parameter that defines this A and B. I'm just not writing explicitly. You can write A and B as certain hyperbolic combinations.
So this is not kind of some coordinate, nothing like that. This is kind of
No. This is not a coordinate. Usually, what people consider here rather a difference between some initial T, which characterizes initial sphere, and some T, which is somewhere when your geometry starts to flow.
Mm-hmm.
But I thought T should be randomization group time. Isn't it time or what?
No.
It's randomization group
I think in this case, you cannot consider really it as time, whereas maybe in our terminology, when no, not here.
So A and B as
it's related to time, but it's related to time, of course, because you are taking derivative with respect to it. This is our G time flow.
Yeah, the point is that this model is randomizable, assuming just these two couplings are running. That's the point, right? So they are
exactly.
T.
So T is a logarithm of scale.
It is related to time, but strictly speaking, in this original Fateev-Onofri-Zamolodchikov papers, I'm not sure they do not consider it as time, but as a time characterizing parameter, where your RG. This is not like in conventional, for people not to be confused. This is time RGs, okay? Where your geometry changes.
Okay, thank you.
Okay, this I already have mentioned, which is even with this axially symmetric profiles that are reflected here, and this is where somebody can see how this geometry develops. So, okay, let me briefly make the outline. So I will first concentrate on the generic CPN-1 construction and how one can in principle do supersymmetrizations. Then I will make restriction to the special case when it's CP1. I will show what kind of deformations are admissible, because again, my interest is we can deform it in many different ways, but my interest is that it is an integrable deformation. The overall model remains integrable. Then I will comment on the Tulip beta function, and starting from this super deformed CP1 construction, I will demonstrate the correspondence between sigma model and a certain QFT description. Okay, and then time permitted, I will comment on some current progress. Okay, apart from this sigma model, now I want to raise another issue, which is, if you want, it comes from the side of the quantum field theoretic view, where I want to recap what the Gross-Neveu models are, what their integrability implies, and what's the role and how do they relate to, how they can in principle be related to sigma models, or more precisely, I would rather say this Gross-Neveu type models. Okay, and I will be more precise in a minute. Okay, so why I want to do this is that in principle, in this QFT formulation or chiral formulation, maybe there is a proper name for it. We can start with this methodology. One can study in principle different target spaces, including symmetric or non-symmetric ones. And the advantage would be that I can, if this approach works, I can use all kinds of quantum field theoretic techniques for computation of observables and properties, and possibly derive new structure that is emergent, including the so-called certain observables that are related to the symmetries. Okay. So by this consideration, as I said, another point, what might be interesting or more convenient in this framework is to study interaction models, which are again can be related to sigma models. In this way, one can find the novel deformations as I already have said, and one can use for the beta function, one can use Feynman perturbation theory without background field methods, and one can proceed with supersymmetrization and so on. Another important point which I want to highlight here is that this target space in this formulation, it might be more proper to see very special class where this target space symmetries, supersymmetries, they agree with the wall sheet ones. Okay, I will demonstrate this. So let me recap briefly what the Gross-Neveu model with n flavors is, which is given by the Lagrangian, and given with this, it can be defined through this Dirac spinner, and where this kind of interaction with intermediate projectors can be defined on. At the same time, and this couple is, of course, can be treated as an interaction coupling. Okay, interaction coupling. So one possibility what I can try to do, as was also observed by Dmitry Bykov sometime before, and even such actually such papers and some work started to appear in the early 80s where people tried to understand what is the spin statistics nature and how it is emerging in these chiral models. Well, in principle, I can rewrite this Dirac spinner split it into wild components, and consider them at the component level. Again, I want to stress this, at the component level to be commutative, not to confuse people, which can raise immediate question. This is quantum model, and I want to switch to later to Euclidean metric, which is not Lorentzian anymore, and in principle should be proceed with weak rotated transformations and so on. At the moment, I want to make the substitution and see what happens if it can be related to the so-called, that's already an old statement where people were thinking of these models in terms of the beta gamma, so-called beta gamma systems. I will come to that in a minute as well. So what I want to state here, if I make the substitution, rewrite it in the given form, I get, I can already notice here that I'm getting something like of the quartic type interaction with the conventional covariant derivative. Here, this U1 residual symmetry, which is in our, if you want, gauge complex gauge group, implies the usual transformations, which again, tracing back at the level of this spinners implies the regular U1 transformation. Well, the point here is that one needs to be very careful if you pass from the classical argument to the quantum level, okay? Because the symmetries, there are many bad things can happen with integrability, especially, and with these gauge symmetries that are emergent, because they can become, and they do become anomalous. So as I have already mentioned, if I consider a complex projective space is a symmetric space, and its associated sigma model corresponds to the bosonic sigma model, it is known to be classically integrable. And since it is quadratic in fields, I have this association, and I can do in many ways, but one of them is, of course, elimination through the equations of motion. I can write this Lagrangian in this compact form, which is already reminiscent of something, I mean this one, which is already reminiscent of something like CPM, but still not quite. What I want to say, there is still one additional local projective invariance that is remaining, which is coming through the so-called Hopf gauge fixing. What it means that, in principle, when I am considering this, as you know, like especially in the CP1 case, which corresponds to the C2 underlying group theoretic description, this Hopf vibration allows me to get one constraint, which, well, from the Hopf vibration of this residual symmetry implies this constraint, which can be, of course, exploited here, and then one would result with just getting rid of the denominator. also, on the conventional side, the CPN -1 is defined through this construction, through this definition, and the kappa plays the role of the same kappas that we have had before. But now, what I want to see here, if I take the difference of my reduced and the fixed model, if I want to look at that, how is it different from the canonical definition of the CPN? I'm acquiring this difference, which of course one can immediately see that this is just anti-symmetric combination, which sums up to in the form level into this configuration, which is nothing but the topological Fubini-Studi form. What does it mean? In principle, it implies that at the classical level, up to, of course, addition of all kinds of topological terms, including like something like theta terms and tachyonic terms, these two setups, they agree. And at the moment, I'm not switching to the quantum level, although it's a separate thing, which can, as I have already mentioned, it would spoil many things, because it also raises immediate issues for the integrability, because one needs to treat non-local charges and local charges, and anomalies arise, and how one can cure this. So now, if I have this provided, I can write, just let me recap the CPN as in the supersymmetric coupling form. There are various ways to supersymmetrize it. Just let me recall that in the regular beta gamma system, which is taken this form is conventional. There are many ways how people, there is the so-called minimally coupled models or supersymmetric coupled models, which in the canonical supersymmetric coupling is just addition at this basic level, addition of the fermionic degrees, okay, as so. But the point is that, of course, I can again recast this into by considering super doublets where U and V correspond to bosonic degrees and C and B are fermionic ones. So when one collapses it to this form, all is good. But from the perspective of the target space symmetry is reflected on the gauge transform for I apologize, this should be for this field. But all this is good, but now one can raise the question, how does it relate to CP? Because these are regular derivatives and not covariant. Very good. So now let me recall also wall sheet perspective of this supersymmetry, which defines, according to the fields, these transformations, according to previous investigation by people. But on its own, I'm looking only at half of it, which closes to the through the corresponding supersymmetry reaction and generators, which are it closes to the 0,2. And of course, when I apply it, it leaves it invariant. Still, I'm talking about, as you can see, in this form, it's like a free theory, nothing special. But of course, when I add up anti-holomorphic counterpart, I'm getting it to the 2,2, which is still a conventional argument. But now, when I want to transit to the CPN, as I said, I want to have the full covariant derivative, which includes the corresponding gauging. And if one wants to prove its supersymmetry, well, it is not just that you can naively replace it by covariant derivative, you would still need to prove that this is super invariant, supersymmetrically invariant. And for that, you would need to define, not to define, but to derive, which follow from all the variational procedure. One can derive the so-called first order constraints, which are associated to the gauge freedoms. And in this case, this first order constraint arises as follows. And one can prove that actually this combination, I apologize, this combination in the brackets is vanishing. And of course, this immediately provides you a supersymmetric invariance at this level. From the target space perspective, this was bullshit. From the target space perspective, let me make just a small note on what it means or gauge on this superspace. Well, effectively, it implies that you have some subgroup which is contained in the GL1/1. And the phase space, as I said before, that is associated. It corresponds to the so-called supersymplectic reduction, where I'm taking this supersymmetric cotangent bundle and mod out this subgroup degrees. Well, in fact, what that means that this initial, before you start any gauge-on, initial global GL_n/n, it breaks down to the certain configuration, group-theoretic configuration, which corresponds to the certain sigma gauge degree in our C cross, which is gauge group. The PSLL, which is diagonal embedding and have this lambda degrees, and the so-called fermionic fibers, which constitute nothing but the n by n traceless S matrices and are constituent here. Okay, now all this is good. I understand Washington supersymmetric target space perspective, but now I want to see my model is still free. I want to make it interactive, okay? From my Cairo perspective, what that means, I want to have some kind of, if you want, current, or more familiar for people who do super conformal field series, like current type, JJ bar interactions. And I can add up to my, if you want, extended or double beta gamma system, where this currents, well, canonically, I think they also, I denote them by mu because they are in this symplectic quotients, they have the interpretation of the moment maps in which people derive some equations of motion. But effectively, what it means, this is current. This is Kac-Moody current in this case, and it is bilinear in the field components that I have already mentioned before, as can be seen here. Okay, and of course, the bar implies the conjugation. But now with one caveat that these curly Ds, these are super covariant derivatives with one extra degree, which is of fermionic nature, this W bar, okay? And well, one can treat this also as a Lagrange multiplier, where everything goes according to the laws, and this W bar will have its own emergent first order constraints, okay? So this provided, I can proceed further and now look, can I implement certain deforming degree? I'm a bit cheating maybe here a bit because I already know something, some relations as I have demonstrated at this bosonic level for the complex projective model, that I can implement certain parameter which will be controlling deformation of my geometry. It means it already at this level I am expecting to have certain geometric relation to the sigma models, okay? What I can do at the same time, as I said, I want the model to be integrable. So I'm acting by certain operator on one of the currents, which is taken this form, and experts can immediately recognize probably that this is the so-called symmetric action of the symmetrized action of the Fateev-Onofri-Zamolodchikov type, or and which contains one deformation parameter, which I was having already above, which was mentioned already in the classical case. But more important is that this operator itself, it is not just arbitrary operator, but it also satisfies the so-called classical Yen-Baxter equation, or if you want modified classical CYV. Modified classical Yen-Baxter equation is the same, but where one would be having on top of this part, it will be having certain inhomogeneous form of this classical Yang-Baxter equation with some quadratic scalar characteristic for the group.
Anton, could you
Yep.
remind me the definition of mu in terms of U and V? How the current?
Sorry.
Okay. Okay.
So this is, as you see, Arkady Alexandrovich, this is bilinear in the components I was mentioning.
Yeah. Okay.
So this is really indeed already at this level. This is kind of, as you can see, quartic interaction model. Okay, but now maybe for somebody who is not particularly familiar with this integrable construction, what it means, I can define this R, this query R. Sorry, there are these notions of the what is called the constant or not or the spectral parameter dependent R matrix, and these RS can be related to this R immediately. Okay, and there is another argument how one can look into this integrable perspective is a proof according to Kevin and Masahito Yamazaki, which states that one implies the other. So if you have this CYB description and you have certain scattering operators that describes your scattering of the model, it immediately implies that you admit a Lax pair formulation, okay? Which in turn, of course, provides you the flatness condition, which is one-to-one in correspondence with the integrability, okay? Where this one form can be defined through this, if you want, extended R matrix, okay? I can comment on this more. So now I want to highlight one important point that now, from now on, I want to switch that this supersymmetrization construction, it can be, it is true in general, for the arbitrary n, but my main interest with a specific example would restrict it to the CP1 model because of many important properties, including the ones that I have been mentioning, the classical Fateev-Onofri-Zamolodchikov model, where these large symmetries, well, I can explain also what it means in this case. They allow you, because in generic, these RG flow geometric equations, they are highly non-trivial in general. And for you having these symmetries of the target space, they reduce those these RG equations to the very basic form. Especially when somebody starts computing the beta function. What I want to stress here is that now, again, my R matrix will be acting as the endomorphism on the two complex space, is again mapping back to itself. Okay, this is the so this is two-dimensional R matrix, as I have mentioned here. So in this case, from our chiral perspective is a special, but also from the signal model perspective, what it means that this target space, it's scalar. Okay, what it means, it also has, the CP1 case has very well-defined relation to the so-called eta deformed models, which also have this or if you want, sometimes it's called Yang-Baxter deformations. From the geometric perspective, it implies that your torsion on this geometry is zero, and it is also as a corollary. You can see that in the scalar prescription, it means also immediately a 2,2 extension, okay, which in higher cases needs to be considered separately, because when you go to n greater than 2, like starting from CP2. You need to consider the so-called generalized scalar geometry. There are treatments also for this, but for the moment I want to restrict to this. And relation but this is again in the purely bosonic cases. There is relation known to these eta deformed cases for the n greater than 2. This is that was looked by the so-called single quantum parameter deformation that was studied by including Dmitry and Marc Magro and Delduc and Benoit from before. But now what I want to stress here is that also I understand the integrable configuration of this model. What I want to state here, I still, in this prescription, this chiral prescription, I still need to prove the supersymmetric invariance, so that my super transformations still apply and hold. okay, one can proceed with, let me maybe skip some unnecessary details. What I want to say is that here, if one goes through the variation principle and combines these equations of motion into the following form, there is a possibility to derive an equation on the moment maps, okay, on the currents, which results in this form and involves, as you can see, both overall scale and this S deformation parameter, which is encapsulates in the geometry deformation. Okay, now you can have holomorphic, anti-holomorphic equations of motion, and you can proceed with this, applying for the demonstration of the supersymmetric invariance of the Lagrangian. What I want to recap that when I apply to this free part, there is no question about this. What you can explicitly check, and it is indeed supersymmetric invariant. The main question is what happens when I check this against the interaction. Plus, this is a deformed interaction. Okay, when I apply to this after variety of procedures and applying the so-called this mu tilde implies the so-called shortcut of the current corresponding to mixed degrees. I am acquiring sorry, these epsilons I think I have shown, but these are Grossman numbers. Okay. And when you apply this, you acquire this, the variation of the interaction, you acquire this commutator. This is the core part. And you can, at the follow-up, you can show that this commutator exactly deforms the two first-order constraints, which arise in similar to the supersymmetric model, undeformed one. Okay.
But what is the reason to expect that deformation is preserved supersymmetry?
Sorry, say it again.
What is the reason to expect that this deformation by this mu should preserve supersymmetry? Should preserve what?
You mean by arrest? This is deformation.
Yes. Why it should preserve supersymmetry? Yeah, that's my.
Yeah, that's what I'm proving here. Sorry.
Yeah, you're proving it. You just guessed it and then you proved it, right? But or you have some reason to.
Yeah. Sorry. Yeah, of course. Very good. I have some reason. Okay, one thing is, again, I want to split. One is integrability. This is fine. But another point is that from the beginning, I already knew that in this supersymmetric setup deformed by this interaction piece, I knew I was able to prove and see that these bilinear configurations undeformed. They can be analogously proved that they are supersymmetrically invariant. And then when I'm acting on one of the currents with this operator, I was expecting my initial conjecture was that if I act, this S parameter will be somehow, if you want, be in certain form could be factorized out. But of course, in general, I was not sure about this. So we proceeded, and it turned out that indeed it takes this form, which is dependent on this first order constraints, which vanish. And as you can see, this evaluation of this delta, it proves the full supersymmetric invariance.
So this supersymmetry depends on the fact that this deformation preserves integrability, or this is
no. It's unrelated. This, yeah. Sorry. Let me say this again. The integrability is one thing, which I can also show via Casal Yamazaki or whatsoever. But what is really important is that this action of the this R matrix, after applying the super transformations on the free part and this interacting part, it takes brings commutator, which arises here, into this form, and this is non-trivial because a priori you don't need to expect that this will take this form. That will be dependent on your first order constraints, which, as we have shown already for this undeformed model, are vanishing. And since these first order constraints are here and it arises in this form, this is what guarantees you the vanishing of this last variation of the interaction. And hence, it implies the supersymmetric invariance of the full action.
Okay, thank you.
Can I maybe insert a comment? I mean, the point was that it was proven earlier that this way, even writing this way, the supersymmetric undeformed model.
Yeah.
And well, you know, in the sausage case, I mean, this target space is two-dimensional, so it's scalar automatically. So that should also be admit a supersymmetric extension.
Yeah, this is what I was saying here. Yeah.
Of natural to try this. Then you ask whether it's related to integrability. Well, so at one loop, the fact that the R operator should be of this form is related to renormalizability, right? It's I think it's basically the only solution of the renormalization equation, which is for R of that form. And automatically, it's the R matrix, kind of by chance somehow. So related to integrability. And but the fact that it's supersymmetric is really related to this algebraic identity that Anton showed with this commutator of RS, this one.
Yeah,
which looks, if you just look at this equation, it's, yes, non-trivial. Why should this deformed commutator be 0? So the undeformed one is 0, but why it should be 0? But it's just...
Again, very naively, any sigma model you can n equal 1 supersymmetrize. If you have a Kahler space, then you can supersymmetrize n equal 2, right? So yeah. if the deformation preserves Kahler structure or some deformed Kahler structure, whatever, then it will be n equal 2, right?
Yes.
So that's actually what you are checked.
Yes, but I mean it's Kahler in the second order.
In the second order, yes. Sorry, yes, indeed.
First order is not that automatically obvious why. Yes, but I think if you start from beta gamma system, so the free part, the beta gamma system, that's automatically admits n equals 2. I mean, if you want.
Free part, yeah. But so in principle, you could just study in general what are the conditions in the first order form. In that form, what are most general conditions of what kind of deformation you can put so that you preserve supersymmetry?
Yes, but the condition is this vanishing of this commutator that Anton wrote, the vanishing of the commutator.
Okay.
But interestingly, in SU2 case, so in SU2 case, so it's 2 by 2 case, this commutator of 2 R matrix RS, so RS acting on some matrix A, commutator RS acting on matrix B is RS dot of commutator A.
I will come to that.
No, but that's not doesn't work for higher n somehow. So that's the reason why it works here. But formally, the equation for supersymmetry is this one that Anton wrote. This commutator should vanish. Yes, it's a break equation. Yes.
Yeah, same thing. I will come into the additional, more general equation, which will be especially crucial in the beta renormalizability. But Arkady Alexandrovich, just one more time. The free part, there is no question about this. What I try to highlight here, indeed, that since you are still Kahler, it admits a priori this 2,2 extension. But when you start deforming this, in general, as Dima also said in the second order, there is no a priori you don't need to expect it to be supersymmetrically invariant. And whether this supersymmetric invariance and integrability arguments are directly related, I don't think so. But what is crucial is, again, to show that this supersymmetric variation of the full interaction piece indeed ends up in this commutator, which needs to be shown to be 0, and that it, in a sense, factorizes out in this action. This of course needs to be proven explicitly. But okay, let me continue. And now, at the same time, once I see that there is something that is already supersymmetrically invariant, what I want to see, I want to gain some intuition, notion of what's the geometric interpretation of this could be. And in order to proceed with this is pretty straightforward way one can get. Oh, yeah. Sorry, I apologize. There's something here. Just a second. There is a way that one can start exploit our constraints that were associated to the gauge degrees, and can make certain gauge fixing, and now redefine our field components in this form. which will be taken after I implement this fixing and the equations, the constraints. So when I plug this in our Lagrangian, what I get, as you can also notice, again, this is a kind of a free part. But then I'm getting all kinds of quartic terms, and mixed ones, and the fermionic one, and so on. What I can do, I can extremize the action with respect to the one of the fields, which is standard, and I can assemble it into the form of this type. Sorry, I'm not writing what the alphas and gammas are explicitly. They are certain functions of the fields and the coefficients. But what is really important here is that I want to pay your attention on these covariant derivatives and then the forms they are taking. On the other side, I know from mirror symmetric arguments that this geometric form of these 2,2 Lagrangians, in general, they acquire some form that this is the metric times the bosonic counterpart. Then you have a follow-up of the fermionic degree, and then you have a quartic block. What it means in our case, of course, what I need to extract is, of course, the metric in front of the du square. I identified that this is exactly the metric of the fourth model. Okay. At the same time, something that stands in front of my fermionic piece is the Riemann coefficient with the contracted with the 2 metric. As a cross check, what I could do when I figure out this part, I also need to capture that in my covariant derivatives, indeed, there are coefficients, if you want, connections, which are defined through this, through the standard D-log derivative, okay? When I do this, I exactly acquire the right coefficients, which they should be. So again, this is not that something that is tuned, but this is the metric that you acquire, and then you start checking whether all coefficients are geometrically consistent, and they are. Okay. Then next, which would provide the equivalence of our super-deformed construction is exactly this geometric form, okay, which so far is consistent. And now, at the same time, from the
how does the Keller potential looks like for this model?
The Keller potential.
Yeah.
I would need. I can show you, but I would need to compute it separately from this G. This is what we omitted here.
No, the Keller potential is some Lie2 poly logarithm.
But this is with some extra terms, yes.
Okay.
Maybe I have it in the extra. Okay, fine. What I want to do next, I want to look into the beta function from this field-theoretic perspective, and for concreteness, I can I can immediately consider the SU2 or SL2 case where my tree level. Oh, maybe I forgot to mention one important thing is that, okay, now since I was having this arrest at the tree level, this is just with a diagram like this, but just with one propagator, okay? And it takes with this tau A, of course, the underlying generators, group generators. The one loop integral and one loop contribution contains these two diagrams. And so the core part is, of course, that it contains some overall diagrams and the possibilities. But one important note, what I want to highlight is that these integrals, they contain the piece, which are, of course, log regulated, if you want, which I denote for AP. And when somebody can ask also, why don't you have some internal loops here? The point is that, as you understand, we are considering 2,2 supersymmetric theory. And the bosonic loops and fermionic loops, they exactly a match, so they cancel each other. This is what you end up finally is exactly this this ladder diagram, if you want. So what happens in two loops? I continue my procedure. I looked into this like combinatorially, if you want. You look into all the contributing pieces, and you arrive that there is a similar integral, but which contains two double commutators, color commutators. And what can be carefully shown through the algebraically is that both of these terms, this one is almost immediate. I think the second one, it takes it needs some attention, but still one can show that they are proportional to this a squared, okay, which allows you immediately to, of course, renormalize. For concreteness, in the SL2 case, we can show that this two-loop contribution arises in this form, and which is, as you can see, this renormalization function is in front, but these dots are, if you want, these are not the previous dots, but these are differentials with respect to S. Sorry. And what arises in this intermediate computation when you do this algebra, one can in different ways, but no matter what, one can obtain the following constraint, which is in principle non-trivial to see from the beginning, that this derivatives of the commutator splits into the into the commutator of the R matrices. Okay. And since we've already shown that this A is an overall prefactor, we can show that this is two-loop renormalizable. Okay, one can ask what happens at higher loops, and this is, for the moment, this is what we are looking into. But I think at 3 loops, we would still be able to show the proportionality, but at 4 loops, something that is, I think was also some time ago already investigated by Dmitry, there is a chance that one will get a regularization dependence. At the same time, people who study similar construction from the sigma model geometric perspective, what they get is they claim that there is certain regularization scheme where you can also make a for loop contribution down to 0. Okay. Now, what I want to highlight again is that now, starting from our full super deformed construction, I want to see the so-called UV limits, UV conformal limits.
Can I ask a question? Maybe you have shown this before. How the RG equation looks like in terms of RS. So obviously this S dot is a function of S, but since this R derivative of S is expressed like that, that means derivative over time of R will be also expressed as like R commutator with R. Sorry, I'm not saying it right. No, my question is how RG equation looks like when expressed in terms of R sub S.
Yeah, I understand. I would need to look up, but
no. So it looks exactly as this equation.
They would be similar to false. This is what I think.
No, I mean the equation is exactly what's written here, along with RS dot. This is the equation basically.
No, but this is Dima. This is with respect to S, and you have a derivative inside.
Yeah, yes, but not for commutator. But I'm asking about not RS just as a function of whatever.
You're asking of this form.
No, but it doesn't matter because log S runs linearly.
Yes.
See, for this equation, log S runs linear. So basically, log S is the RG time. It doesn't matter. Differentiation with respect to log S is the same as differentiation with respect to RG time. So it's the same equation up to coupling constant or something. I mean, there's a coupling constant in front.
No, I think we should
and higher order corrections will be, say, cubic in R, quartic in R, and so on.
Okay, okay, yes, okay.
But no, I think you still can extract the different. This is differentiation with respect to S, but S is also running, and for that.
Yeah, but it will
extract
be
a separate
multiplied by
equation.
S dot. Yeah, you should use some other derivative. Indeed, it should be
Yes,
prime.
because
Yeah.
also no, I mean also this derivative RS dot is not derivative with respect to S, it's derivative with respect to of log S. But so
yeah. What I'm saying, this is log S. I can write it explicitly. Yeah.
Oh, okay.
So what I want to say, just in addition, is that indeed you can split this, and you out of this you will also obtain. You can get a separate equation on the running S. Okay. From starting from here. So eventually, this is like it can be a set of equations.
yes, and this is also the same as Nam's equation. I mean, this one.
Right, exactly. But also, maybe if I can, Arkady Alexandrovich was asking before, these constraints that we get exactly in the derivation for the Tulip renormalizability, it can be used also here instead of this. And it also implies as you can see, the supersymmetric proof of supersymmetric invariance in this case is related to this constraint, or it can be just used as on unified basis, and they're related. I mean, supersymmetric invariance and Tulip renormalizability, by which a priori was not obvious at all. So what I wanted to say regarding
they must be related, because otherwise you will not have. You will need more couplings, not just
exactly. So what I want to say, there are two interesting UV conformal. Let me briefly mention, since I'm probably running out of time. But the one is reduction of the when your S goes, sorry, in a scaled in the scaled way it goes to 0. By scaled way, I can explain what it means. You got a model which lies on whose target space is cylinder. So of this form, and if actually, as you can see, this is like of the free type, one can claim what's special or interesting about it. And well, the point is that there are many interesting things that could be related to the so-called Sine-Liouville supersymmetric Sine-Liouville models. But this is like a separate question. I can comment if somebody is interested. What I want to say, and there is also another limit, which, but before taking it, you need to just S rescale our Lagrangian, and then you will acquire the form of this, where you can see that your U's are now appearing in the denominator, and this is like a kind of a, you can already see that this is like kind of a singularity. What it means that you are you can see that you are around the tip of the so-called cigar. When we are having the sausage, when you flow into closer to the tip, you can acquire singularities. So this is the so-called super cigar model. Now, what I want to say with this correspondence is that we have the super deformed complex projective construction. And we acquire on the sigma model side, you can get from the geometric perspective the super cigar model, and you can get from this comes from the geometric interpretation of this form. I apologize, maybe I run too much of this type. Sorry, of this type, and at the same time you can get it from the chiral Lagrangians that we were proposing from the beginning. And we get we claim to get the correspondence between two, and where super cigar, maybe there is a better name, but it relates to this scaled GN model, whereas the super cylinder corresponds to the so-called super-Thirring model. Or if you want, I think that this is something that has been studied also in the past by Friedan and people, which relates to the so-called double beta gamma ghost systems. Okay, and what can we do in order to confirm this? We can compute, for example, some correlation functions. Let me briefly mention what it means from the supersymmetric Thirring model side. If we consider the 4-point correlator, I can comment why lower point correlators in this case, if you look into the bosonic one, they are trivial. So if you look into the 4-point correlator, you can write from the perturbation theory, you can write this integral as follows, and redefine it by taking the integral. You can get the conventional cross ratio, which is SL2C invariant. Okay, so you can recast in this one. But now you can ask what happens when I go to L. Since we have this advantage of the loop cancellation, you can go to higher loops, and this becomes nicely the combinatorial exercise. So in L+1 loops, one can write the integral accordingly, which the middle nodes are summed correspondingly. And what one gets when assuming the contribution that we were getting from the lower level, we can write a recursion, okay? And recursion is taken form whose resolution provides you for the L-loop contribution the following form. So this is again SL2C cross ratio to the power with a certain coordinate dependent prefactor. So for in order to get the corresponding 4-point contribution, of course you add all, and you end up with something which is cross ratio dependent, which one would probably in theory anticipate. From the supersymmetric supercylinder model, what can we do? We can acquire our Lagrangian, and probably as one would expect, to proceed with the vertex operators, which is the right thing to do. And but here we would need to define this elementary field, our elementary fields in terms of our initial field B component, B and C components. So this 4-point function, from this perspective, you can write immediately the path integral is taking this form, where these W's are arising as I'm shown here. So I'm probably not writing explicitly, but what is core important that we can bring it into this form. What else you would be doing is that now you can derive the equation of motion and see what do they look like. After plugging in back and doing some algebra, we can confirm that this integral immediately collapses to this form, which is again with a prefactor which is coordinate dependent, and this cross ratio is taking exactly this form. So now by looking again into something that what is got to for the 4-point function to L loop level to arbitrary loops, and comparing the results, we see that these two 4-point functions exactly agree on both sides. Well, in principle, this is work in progress. One can consider also mixture of the Fermi degrees, but then these factors will take the Kuba-Nielsen type. And then in principle, one can proceed with the same perturbative combinatorics. Okay, let me sum up. What we have obtained is that we have considered this field-theoretic view on the supersymmetrization of the deformed complex projective class. And we have derived, before what we have not found, the novel super-deformed CP1 model, which must be related, of course, related to what is called the n equals to Liouville classes and Landau-Ginzburg model, but this is, again, currently under investigation. So we have checked the beta function to two loops and its renormalizability. So to two loops, still, it's probably definitely not sufficient to say that this is one loop exact, but this is to an argument forward. And we have investigated the conformal UV limits and find full consistency by computing the 4-point functions. Some work in progress that is related, of course, the proven actual one loop exactness and studying the RG flows. And the regularization scheme problem seems to be already seen several ways on how one can address this. Probably the geometric form could have some advantages, but we still think that there should be some schemes maybe related to the covariant regularization that could be of help. Another extremely important question is that this consideration of the sigma models and toric varieties, or squashed ones, which is effectively nothing but the, for example, an example of this is a sausage model. They have mirror duals of the so-called n equals 2 sine Gordon models, or refined Toda. This is the well-known Landau-Ginzburg model where people need to define the corresponding potentials and see how these models can correspond to each other. And one interesting thing is that here one can consider also the so-called relation to the fermionic black holes, which is also already known work, but in our new setup, the interesting relation is of course to this piece. But one can study relation to the possibly some new Kazama-Suzuki perturbations. Or another important question is, of course, it's in principle related to the previous two, is the GLSM formulation, where one can compute the different observables. All this, of course, goes along the lines of black hole spin chain program, and of course, there are other generalizations go into higher end, and how the generalized scalar geometries can be implemented into our settings. That's a separate question. Or if other supercassette targets, or especially these bow varieties, can be also interpreted or implemented in our framework. Yes, and of course, anomaly relation and the cancellation mechanism can be studied in our framework as well. This is follows the question. Many more. So I stop here. Thanks.
Thank you. Are there any questions?
Yeah, I have a question. So the first question is whether this first order formulation is actually equivalent to the second order formulation. Well, maybe I'm a bit confused about the following fact. There was this discussion by, I think, Losev, Schiffman, and somebody else.
Yes, and Gamayun probably.
Yes. So what they were originally confused about is that indeed, in general, when you integrate over some auxiliary field to go from one formulation to another, you may get determinant which actually contributes to the beta function starting at higher orders. So what happens in this case? Do you think these two formulations are equivalent, or?
Two formulations, you mean what they consider?
Yeah, like formulations is two-dimensional sigma model.
I think in our case,
second derivative formulation. In our case, in your case, you think it's just algebraically trivial.
I think that you can, as I have shown, like at the classical level, you can find the exact duality.
Yeah, well, classical level is not an issue. Yeah.
Yeah. But if you go to quantum level, I think, Arkady Alexandrovich, there are many issues because what happens if your same original sausage model, if you start adding theta terms, because they were contained. And what happens at the quantum level with this? What if you add some other topological terms? I don't think in general these two formulations would be equivalent.
Well, this would be instant-on corrections, whatever.
Yeah.
At perturbative level, I wouldn't worry about that theta term. No, but okay, so that's one question. Second one is about scheme dependence, just at the level of, in the first order formulation, which may be, in this case, quite more rigid somehow. And there may be preferred scheme in which this equivalence actually holds. And in that scheme, maybe indeed there are less higher order, higher loop correction.
Yes.
Because in general, if you just take Kahler n equal 2 model with some Kahler potential, at higher orders, there are higher order corrections to the beta function. You can deform Kahler potential, but that doesn't mean you have a local redefinition of the metric or local equation.
Yeah, well, I absolutely agree with this.
So that's why Calabi-Yau is not exact solution in general. In some sense, you can argue that there should exist exact deformation, which solves loop-corrected beta function, but just original Calabi-Yau metric will get deformed. Yeah, I'm just, how how to
Well,
say.
that's for sure. But you're worrying about here about what?
I'm suggesting maybe. So in general, Kahler model with some Kahler potential will get that potential deformed in some complicated way in general.
Yeah.
But there may be special scheme for particular Kahler potential, for particular, not generic.
I absolutely understand.
Where that doesn't happen. So maybe
but the point is that, if I'm correct, maybe just for me also to know, there is no unified, if you want, prescription on how you can construct these deformations of the Kahler potential, right?
Yeah.
Or you're saying you can somehow, I'm not sure, bootstrap.
Yeah, well, in general, the RG equation for the Kahler potential will be non-trivial with higher order, with all corrections from up to whatever number of loops.
Yeah, but this is where symmetries help you, right?
Yes, but indeed it may happen that for particular model, it may be having less.
Yeah, I see your point.
So maybe can I also comment? So first of all, yeah, I think it's very likely. I think that there is, maybe for these models, there is some scheme where you can actually prove explicitly that it's one loop exactly, even in the deformed case. I think it's pretty possible. Actually, related to this, of course, we know that in general, indeed, at 4 loops, there is this correction that cannot be killed, right, by rediff in general. But for example, I think in some recent paper, there's Alfimov and Litvinov, they show that for the sausage model, actually, you can kill the 4 loop correction by in supersymmetric case. So of course that's a fine tuning argument. So of course we would like to find a direct scheme where it would be automatically true, but I think it's likely to exist.
And it's specific to 2-dimensional target space.
Definitely.
Yeah. So the target space is 2-dimensional. That's why it's possible.
And regarding your first question, so I'd say that this, at least in supersymmetric case, it should be exactly equivalent. So also first of all, even in this Lossev et al. Schiffman work, they have much better behavior in supersymmetric case. Yes, actually they use supersymmetric thing as a regularization, yes, for their bosonic models. So, but besides, indeed it is true that I think the dilaton is the logarithm of the quadratic form. When you integrate the over the v variables, right? Your interaction is a quadratic form in the v variables. So in general, the dilaton is determinant of the quadratic form, of this quadratic form. And but the point is that in the CPN case, this determinant is sum over UA squared, modulus UA squared. Yeah. And sum modulus UA squared is not a gauge invariant quantity with respect to C star. So for example, we can set sum of UA squared equal to 1, which is what people usually do. Yes. In CPN models, right? Sum of UA squared is 1, so which when the determinant is just 1, therefore. So in general, when you don't use this gauge, there is some. I mean, the derivative of the dilaton always comes with some additional gauge field, which compensates that C star action, as I showed in some first paper I wrote on this stuff. So, but it all works out. At least at 1 loop, it all works out. I mean, in higher loops, of course, it's a bit of a guess, or I don't know. Yeah.
Yeah. Also, maybe just a very quick note is that in this work by Litvinov and et al. And Misha, their claim is that, first of all, this is not from this field-theoretic perspective, but they work in purely geometric framework. And what they do is this regularization schemes that they find is exactly turn-by-turn tuning. And they find one peculiar thing is, of course, as you probably have seen, that these coefficients in the regularization scheme, they are just constants. And this is, but they have checked this up to 4 loops, but they're not sure if how far it holds. They claim that they have this constant scheme order by order that can be developed, but so far there is no proof, I think. And about this loss of Gumain-Schiffman, I think, Dima, this is only when they restrict to this CP or vector fields linear models. This is where it works. In the geometric setting, I think that they show that they already have issues at the 2 loops for non-supersymmetric models.
Well, I think they resolved their issues by adding supersymmetric fields and basically by
supersymmetric, of course. But
basically by
initially
generalization, I mean they add additional fermionic fields and then masses.
Yeah. So there is no question about supersymmetric, because before they were claiming that they have this argument and the non-supersymmetric level. But
yes, actually, their way of the way they do calculations is exactly the same argument as the way you calculate chiral anomaly, right?
Right.
Called the Wheeler's field. But actually, I had a question to Arkady. Why do you insist that it's only for two-dimensional target space?
No, that's what Litvinov they were doing, because for 2 dimensions, curvature is very special. Everything is expressed in terms of Ricci scalar.
Yeah.
So higher order, lots of higher order invariants are actually reducible to simple powers of Ricci scale.
Mm-hmm. Yeah, and in this setup there is a challenge with supersymmetry for higher n. So this equation for RS, commutator of RS doesn't work for higher n. So it's not possible to supersymmetrize in this way for higher n. And for higher n, we also know it's generalized Kahler, not Kahler anymore. So it's somehow interrelated.
Once you have B menu field, it becomes even more. It will be non-trivial already at 2-loop level. More non-trivial. No, but yeah, it's higher end.
Maybe it would have been useful if it was possible to reformulate it in this Gross-Neveu language, but like I say, there are issues with supersymmetry in that case.
I don't think we also have a clear picture what the B field would have as the addition correspondence in the chiral formulation. That's a good point.
Yeah, in general, these supersymmetric Gross-Neveu models seem very kind of exotic in a way. I mean, they really rely on the fact that we gauge part of the symmetry. So, for example, it's not known how to formulate them in superspace, for example.
I'm sorry, I need to disconnect. Yeah, thank you very much for your talk. Yeah, thank you, Anton.
Yeah, thanks.
Can I also ask the following question, a simple one? You started with the usual sigma model and you kind of supersymmetrize it. After that, you easily calculate multi-loop diagrams like in supersymmetric way. The question is, can you extract a beta function in the original model kind of by subtracting the fermionic diagrams, like in easier way than you would do it in the original model? I mean, to use this, yeah.
So, you probably would want to. You mean like in the original FOS that would be symmetrized, but then you would be subtracting the fermionic contributions.
Yeah. Kind of. Can you use all this machinery as a calculational tool for the usual non-supersymmetric models? Or this is more involved, will be more involved than...
I'm not sure. I don't know. It sounds for me a bit artificial in a sense that anyway, you see this advantage of the supersymmetrization is that you can remove unnecessary contributions with internal loops or whatsoever. But here you would be like precisely bringing them back.
Yes. So the question is absolutely different. Suppose you have a sigma model which is non-supersymmetric and you want to calculate like higher loop in this model. And you kind of, the first step you can do is supersymmetrize it, calculate many loops. But then the problem is to subtract something.
Yeah, I understand. That's exactly what I'm saying. So I understand your point. But in principle, you can write those, but this is, to me, maybe sounds a bit of double work. I'm not sure whether it would be advantageous. This is probably your question.
Okay. Yeah. This is the question. And also, can you explain your discussion with Arkady Alexandrovich about the duality between the model? So you have a nonlinear local substitution into one model, except you change terms and you obtain another model, right? And so Arkady says that this changes the kind of, this provides a determinant that changes the measure. And so the quantum models may be unrelated to each other.
Well, I would say that quantum definitely don't need to be related because, like, if you remember, as I said from the beginning, because first of all, we use a lot of gauging, okay, and these residual symmetries at the quantum level, they can become anomalies, and then you would need to treat these anomalies separately. You would need to cure them. But
but if you have two models which are related to each other by a local transformation, then you have a problem with measure. This is the only problem. Like the gauge symmetries are Fateev-Popov determinant in the measure. Okay. So the measure changes, but the detail that I don't understand is the following: why you have a freedom of choosing different measures, right? So you can kind of always choose a measure in such a way that the two models will be equivalent on the quantum level as well. Well, equivalently, you can add contact terms to the Lagrangian, like suppressed by h bar, by Planck constant. And this is also a freedom in quantizing the theory. So you can quantize one theory in one way, another theory in a way which is kind of in accord with the first quantization, and then they will continue to be.
I think I see your point, but again, you see the map like which I was showing here, where you can surpass from this from something like this, like this to pass to something that looks after all like this. I don't think there is a clear picture of what it would mean at the quantum level. This is first. Secondly, at the measure level, you mean like Fateev-Popov measure for which model? You mean for this chiral model?
I mean for both in very generic ways. You have one model, you have another model, and you have action, and you have a measure which includes Fateev-Popov determinant.
I understand schematically, you mean, but I'm saying think that this map is of this form here, or it is as trivial as that. Because in order to pass from something that is given by this QFT with chiral symmetry or super chiral symmetry to here, well, these are some nonlinear transformations.
So you
I see your point. So again, the quantization on both sides. I'm not sure what if this map holds at the quantum level at all. This is what I understand your point, but I'm not sure what it means at the quantum level.
No. So I mean, I clarify. I mean, so in the supersymmetric case, we have basically no doubt that these are equivalent models. Like we see no source of discrepancy.
No, Jim. He's asking about the classical one. The initial one. If you supersymmetrize, there is correspondence.
Yes. In the bosonic case, there are very subtleties. Some of these have been investigated by laws of Gamayun, Schiffman, and there are subtleties. It's not totally clear what's the end point of this.
That's what I'm saying.
Yeah, but basically, Dima, I'm asking Anton about these subtleties, where they come from, because from my viewpoint, very naive viewpoint, okay? So you take your model, you change the variables in a nonlinear way. This is not allowed in the quantum case because the measure changes. But you, on the other hand, you always can add a counter term to the action. And kind of, I had an impression that you kind of take a nonlinear transformation to another terms, and then you should quantize your model in a very particular way with very particular contact terms, then you will get the model which is equivalent to the original one. Why this logic doesn't work?
So if you're saying yes, so there is of course a determinant in the change of variables. This is that is the question about the dilaton that Arkady was asking. So yes, in general there is some additional dilaton term that has to be taken into account, and I don't think it's known how to do it at one loop, but higher loops, I'm not sure it's clear how to do it. So But in supersymmetric case, it all cancels out somehow, and it's a
so you can change your variables. You get a determinant in one description, but in another description, I will tell you that I just subtract this determinant as a counter term, and I get two equivalent models. Can I do that?
Well, I think. Well, I think
this is another definition of
the dileton will not be equivalent to the one with the dileton. So I mean,
you mean in non-supersymmetric case? This is what you're saying.
Yeah, even in non-supersymmetric. Yeah, I change the variables. I get the determinant, kind of logarithm of this determinant is added to the Lagrangian. But then I say that on the I will quantize the model in such a way that the determinant is not just the integration over all fields, but it includes the factor. Yeah. Then the models will be literally equivalent, and I will be happy. This is a kind of very special quantization.
Yeah, I understand in principle it can exist, but the point is that then you would need to cure also how you fit anomalies, right? On both sides.
Yeah, yeah.
If you can match this
should
and
be
provide some data on your quantization scheme, in principle, yes, but not in general.
Okay. Okay, thank you.
Thank you.
I would imagine that the model with a dileton and without a dileton will be different. So I mean,
yeah.
At least I don't know. In string theory, the dileton is the coupling, string coupling, for example. So you're saying, what if I set string coupling to 0? This will be different from string coupling non-zero, let's say.
Well, I think he means some intermediate level. In general,
maybe. But I mean, precisely to avoid these subtleties, yes, these are important subtleties and they're interesting, but precisely to avoid them, we have started from the supersymmetric case. Actually, maybe there's a simpler example. So Anton was talking about the super-Thirring model. So it's actually known that the Thirring model itself, the usual Thirring model, has a long history of like wrong solutions. They have a long history. Various authors wrote wrong answers for the Thirring, for correlation functions of Thirring model and so on. So in the supersymmetric case, this is because there are certain ambiguities that one should deal with, certain subtleties. In the supersymmetric case, they precisely disappear. So the supersymmetric Thirring model is a perfectly simple, nice model. So this is one reason why we study the supersymmetric case, because it's free of these subtleties.
Also, you know, just a small add up. Also, at the level of integrability, when you need when you have two types of the local charges in involution and non-local charges, which can be associated to the internal symmetries, which are associated in terms, it doesn't matter, quantum symmetries, the so-called. But those you would need, those are associated to the anomalies. And in supersymmetric cases, those anomaly cancellations, they occur immediately. And if in general case, like you say, for the non-supersymmetric ones, you would need to know how to deal with this. Still there is, like Dima was saying in this in the string models, with certain topological or linear dileton contributions. Those ones have emergent anomalies, but not at all levels. I'm not talking about gravity models. Like those have separate anomaly cancellation mechanisms. But in principle, you can. But in general, it's not known.
Yeah, so it's a good comment, Anton, that indeed there's also problems with integrability in the purely bosonic models. So there are no anomalies in integrability in purely bosonic models. And probably it's related to these subtleties that you asked about. So this is all, it's not really clear. The story is not over there. So it's clear that in the supersymmetric case, most of these problems are gone. And this is the clean, nice, clean case. Kind of. That's the upshot of our work with Anton, our conclusion.
Okay, thanks.
Thank you.
Okay, I guess it's time to wrap up. So thank you very much.